So, dear student, Assalamu alaikum everyone. So, I hope you are fine and doing well. So, in last lecture which I have uploaded, there was some issue of regarding the XE is not working. So, I just come up with the solution how I have to perform this on Zoom. So, I just come up with this regendal animation. I mean to say AES, Advanced Encryption Standard Animation, how the whole things is working over 128 bits of plain text and 128 bits of key. So, dear student, this is one of the animation, and if you want to see all these steps, it will be quite convenient for you to implement all these steps over some digital medium, like it may be image, audio, and video. If you can apply this over to some digital medium, and the simplest digital medium nowadays is digital images, and the images consist of different types like RGB, CYM. There are the different color spaces, but generally people are testing and authenticating their any cryptographic algorithm over color image of type RGB, and it consists of three layers. So it will be quite convenient to apply this, and you can take any 16 pixel of any you divide the whole image into a 4 by 4 chunks of 16 pixel, and these 16 pixel, one pixel is fundamentally consists of 8 bits. So in that way you can say, with the help of 4 by 4 matrix, and in which we are saying it's a initial state. So you have to pass all these 4 by 4 matrices, which you have to uh, basically convert a very large image, like say you, if you have 256 by 256 images, then you have to divide it hours divided by 16. In that, if you divided 256 cross 256 divided by 16, you get some number. So in that case you can say you need uh, if you can divide like you need two, if you have, say if you have 256 cross 256 grayscale image, and if you divide it by 16, what does it means? It means you need uh, let me calculate it first, you need let me do it. Mm, so wait a second. So if you get 256 into 256, and it is divided by 16, so you need 4096 basically 4 into 4 blocks, means to say you need in the total number of pixel in 256 cross 256, like I mean, so I just take one layer of digital image. In that case the total pixels are 65,536. If you divided it by 16, I mean to say 4 by 4, so you just get 4096 blocks of 4 by 4. So in that case, each 4 by 4 block is consist of 128 bits, because if you can say one pixel is consist of 8 bits, then 16 pixel into 8, it is 128. So you have to convert your 256 cross 256 image into 4 by 4 block, and you need 4096 blocks of 4 by 4. So dear student, in that case, to each and every block you have to apply AES and take a 4 by 4 any cipher key as an initial key through that 4 by 4 key, which is again consists of if one first element of key is 8 bits. In that case, if you have key is of 4 by 4, order of the key is 4 by 4, in that case you can say you have 128 bits key. So let us come up with some animation how your digital basically digital digitally how AES as a whole how it behave on some state, I mean to say on some initial data set like Regendal or AES, Advanced Encryption Standard animation using 128 bits. Dear student, I just take this animation from one of the tool available online. It's Crypto Tool, and I just take this animation from Crypto Tool 1. You can easily download this Crypto Tool 1 as well as is another form updated format is crypto tool 2. It's also very good. I'm not going to waste your time. Let us start, and I'm highly thankful to uh, Professor Dr. Christoph Manel from Germany. That Mainly he is the author of and he is basically the developer of this website, and he is quite good, and he is quite expert in teaching. And sir, we are quite thankful that for this animation, and now I'm using the animation of one 28 bits key. So let us come up with. Generally, the encryption algorithm is consists of more generally. It consists of basically five component: plain text, ciphertext, key, and then one encryptor and as well as decryptor. So there are fundamentally five components of any encryption algorithm. So let us come up with some basic. So each and every things in cryptography is in the form of like in block cipher mainly, it is in the form of some blocks. So your cryptographic algorithm, mainly block cipher, take data in the form of blocks. So this, if you have very long say string of bits, so you have to convert this into a 128 bit chunks. If you have let us say 256 cross 256 digital image, then you have to convert first into a pixel, and then pixel are converted into a bits. So in each and every there are number of bits in 256 cross 256 digital image. So you have to convert each and the whole very large stream. If you convert the pixel into a very large one-dimensional stream, then you have to take chunks of 128 bits. So first say you have take first 28 bits, then rest of other second 28 bits, and then third 128 bits. In that case, you have to divide the whole of one dimensional array of bits into a 128 bits chunks, and then 128 bits are converted into 4 by 4 matrices. And this then each and every element, if you have 128 bits and you convert it into 8 by 8 bit chunks, so you have 16 chunks of 120, I mean to say 16 blocks of 8 bits. So you have in this case the student, I just convert the each block of 820 128 bits of each blocks is basically consists of 8 bits in 128 bit of larger block. So I just convert the 8 bits into a hexadecimal notation, or you can convert it into a binary to decimal, that it ranges from 0 to 255. So I just take one say initial state, which is consists of, if you convert if I can give you one assignment, if you don't realize what does it mean, so you just put these all these element in a MATLAB, and then just draw a hex to binary or a hex to decimal notation. So in that case, in each and every element of this basically 4 by 4 matrices consists of 8 bits, and in that case, if you sum up all these bits, you will get 128 bits. So dear student, let us start with this. Is one of the initial plain text which you are going to basically encrypt. So this is one of the cipher key of 128 bits, and the initial vector means to say plain text is also consist of 128 bits, which is to be encrypted. So this 32 is fundamentally consists of 8 bits. This is 1 byte. So dear student, let us come up with initially this is also 128 bits key, and this is also 128. Due to visualization or due to space constraint, we just convert the 128 bits into a hex notation in order to write it in the form of 4 by 4 matrix. So in the form of 4 by 4 matrix, it is quite convenient to we can see, and it is quite visible. If you can write 128 bits of each element, that it will be quite what you call is quite not very good. So in a visible way, we just convert it into a hex notation. So in order to easily place it and basically save the space. So dear student, let us go into second. Basically, encryption procedure is consist of for 120. Basically, we are is performing simulation of AES over 128 bits. In that case, dear student, we need 10 rounds, and for each round, we have to generate a sub keys for each round with the help of initial key. So, and you know it quite well that each round is fundamentally consists of 4 transformation. This is sub byte transformation, shift row, mix column, and add round key. These are quite fundamental. So let us start with how the encryption work in AES. So these are one of the animation. These steps are here. You can see for each round, these 4 fundamental steps are performing. In that case, if you can look over here, these are quite fundamental steps, and these are performing. And in that case, you can see over here the in and through animation, you need just you initial round you just add a round key with given plain text, and then perform the whole the sub byte transformation. I mean to say substitution boxes. So dear student, these are basically these two steps are fundamentally qualify for diffusion, and this steps the first step, which is sub byte transformation, this is qualify for confusion. And in modern blocks have these add round keys is one of the another additional steps. So you can see these through these 4 steps, dear student, we easily authenticate that our modern block cipher consists of confusion as well as diffusion capability, which are quite fundamental while designing any robust crypto system. uh, by the idea, one of the principal idea of Claude Shannon in 1949. So you need confusion as well as diffusion in order to make a very strong block cipher. So this crypto system qualify for that. And let us start with some how this fold transformation will work in AES. Like these are four transformations. We are more or less familiar with these, like how individually these will work. Sub-byte transformation. Say we have this data set. So how sub-byte transfer? This is one of the substitution box. The first element tell you about row, and the second element tell you about the column. So I just index it from 0 to F. Basically, this data is in hex form. So my index in this table is from 0 to F, and this is all why the column range index is from 0 to F again. So you can convert it into a decimal too. Then in that case, the index will be of row will be from 0 to 15, and the column is also 0 to 15. So dear student, don't you bother about. If you don't realize, then you can convert this 63 7C into a decimal notation. These are all basically component of substitution box, and you can see over here no element is repeating over here. This clearly reflect this substitution box is bijective. So if you convert this element from hex to decimal, the range, the all element will be from 0 to 255, and these will be uh, arranged in a random manner. It should not be arranged in a ascending, and it should not be arranged in a descending order. That basically break the here. You can see over here there is no pattern. If there is a pattern, then ultimately the confusion capability of the block cipher will be compromised. So it should not be there should not be some pattern. It may be in ascending, it may be in descending order, and moreover, it should not follow some pattern. So you have to realize this while constructing any substitution box. It should not be it should not have some fixed point. So keep this thing in your mind. So let us come up how to use this substitution box. If you can look over here, this is 19 is this is 19, and the first element tell you about row, and the second element tell you about the index of column. If you can see, this is this one this row, and 9 this column, and just pick this element D4. So I place with, and the same I did for all other element of this chunk, which is plain text. So in that case, if you can see D4, this is my after applying substitution box, I get this. So the second step will be, tell me about it. What will be the second step? Yes, this is shift row. So dear student, from last step we get this result after applying substitution or sub-byte transformation. So in first row remains same, then in second we'll have to apply rotate our 1 byte, it means one rotation. In third row we need 2 byte transformation. In third we need 3 rotation. In that case, dear student, we perform uh, shift row. And this third most important thing is mix column. So from last output of shift row is we get this state after applying shift row. So the after applying column, so you have this first 4 plus 1 column vector, you have to multiply it with 4 by 4 matrix. So in that case you will get this one, another 4 plus 1 column vector. In that case, you have to apply for each row of the state apply the basically multiply with forecast for matrix of these each column. So in that case, dear student, you will get other component. So this is basically the output of last mixed column operation. So how to add round key? If you can look over here, this is our round key. Um, Produce as a round key 1 during the key scheduling that will be seen in slide number 19. So let us come up with how round key will work, add round key will work. This is a fourth transformation in substitution box. So I just take one first column, and the first column of the round one key. So I just XOR it, I'll get this one. And this similarly I perform for all three column vector of the output of mixed column operation. The output of mixed column operation that I get from this. So after applying rounds in my basically the output of mixed column operation is also changed after applying add round key operation. So in that case, these transformation are applied to state for 9 more rounds. The final round does not include the mixed column transformation. So here you can see in that case after sub-byte transformation, that is first after sub-byte transformation we get this, as we can see from previous slides, and after applying shift row we'll get this, and after applying mixed column we get this, and then the finally we'll get this state. In that case, if you can look over here, so for same we apply the same steps for each and every what you call it uh, as a in for each and every round we have to perform these four operation, but in last step we don't perform a mixed column. In that case, dear student, you will get these all these results, and the ultimately the output, that is encrypted message, will be this one. We start with 4 by 4 plain text, and the output will be this one. So these are just our ciphertext, and how the key scheduling or key scheduling will be performed in AES, how for with the help of one key you generate key for each and every round. So uh, let us start with the keys scheduling problem, how it will work. So you have fundamentally cipher key, which is placed in our third or fourth slide. So how we can generate for a key for first round, second round, third round, up to 10th round. So if you can take last this one, the last column of the initial cipher key. This is, we call it, this is one word. Uh, as a whole, this is called word. So you have to rotate this word vertically. So you just rotate this vertically, and then apply sub-byte transformation. After applying vertical rotation, and then apply sub-byte transformation with the help of the same substitution box that we have performed in our first step. In that case, our and then XOR it with any of the round constant. I just take for this is my I just take this one, then rotate this element, then apply. After rotation, I apply substitution box. Then the output after applying substitution box is XOR with this first column of this in cipher key, initial cipher key, first column, and then XOR it with round constant 4, that is this one. So in that case, the student, I get this forecast on column vector. I just plug it over here, and same I have applied for first column. I have applied substitution box, and for rest of the column, I have just XOR this with previous, like you can say, previous column vectors of this in a cipher key. In that case, I get 88, and the same I just ignoring this one, and then this is completely the round key for first round. So for second round, before getting this one, I just take another the last column vector of this round key, first round key, and then rotate it vertically like this one, then rotate it vertically, then apply substitution boxes, this one, and then I XOR this with any round constant which is given over here. This is round constant like this one. So dear student, if you can look over here, I get this, and then similarly I perform the same step of XORing this operation with last key, then I get this one. So similarly, this is round around 2 key. So in that case, we have to perform same steps 10 times, and we will get 10 different keys for 10 round. So these are just key scheduling problem. I just explained this because this is quite important for you being a cryptography students. So it will be quite convenient for you to implement this encryption algorithm, and these open AES advanced encryption standard is open source, and I mean to say open source. I mean to say this is available. Its code is quite available in MATLAB, even in Mathematica, even in Python, in different languages. You just take it and perform all these steps over some digital medium. It will be quite convenient for you to take one very small images like image which is consist of 16 pixel. It means it has one chunks of 128 bits, and just apply this AES on this very small image, and see how each and every steps is performing in the hidden structures of AES, how it will work. That will definitely enhance your understanding regarding AES. And till then, please stay at home, and may Allah bless you all. Allah Hafiz and goodbye.